Hello everyone, welcome to Shriyana classes. In this video we will be talking about the number systems and all the parts associated with a number system for class 11. So first of all, when we consider any number, suppose 213. So 213 we call it as the decimal number system, because up till here all the things which you have learned from your class 1 and all the mathematics you have done are in decimal number system. So starting from the base decimal number system, we are going to learn that what is phase value and position value. So the 213 can be written in the form of 2 into 10 into 100 plus 2 into 100, then 1 into 10 plus 3 into 1. So basically it can be written as 2 into 10 to the power of 2 plus 1 into 10 to the power of 1, then 3 into 10 to the power of 0. So this is phase value and this is position value. So a number contains two parts. One is phase value and the position value. The phase value says that what the number is present at that current position, and the position value defines that where the number is sitting around. Now we are going to see that what are the different types of number system. So depending upon the base, which we are going to talk few moments from here, that the first thing is that binary number system. So binary stands for bi means 2. So it deals with just two numbers, ones and zeros. Then comes your octal number system. So oct means 8. So it deals with 8 numbers starting from 0 to 7. Then comes your decimal, which is the normal number system which everyone uses. Decimal number system. So deci means 10. So starting from 0 to 9 without any symbol repetition, there are 10 numbers, and the last one is your hexadecimal system. So hexa deci means 16. So starting from 0 to 9 it becomes 10, and the rest of the 6 numbers cannot be directly represented in the form of the zeros and nines, 0, 1, 2, 3 or 9. So it has to be different. So it is represented in the form of A, B, C, D, E and F. So as we all know that 0 to 9 as usual, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then 10 is represented as A, B is represented as 11, C is represented as 12, D is represented as 13, E is represented as 14, and F is represented as 15. So in terms of this 10, 11, 12, 13, 14, 15, since we cannot use 10 as zeros and 9 are already has 0, 1, 2, 3. So basically 1 0 means what? Repetition of 2 digits. So basically, since we cannot do that, we have to make difference of symbols. So that is why the decimal number system starts with A, B, C, D, E, F for the rest of the part. Now we are going to look forward into the part where we will be seeing that how to convert a binary number system into octal or decimal and hexadecimal. Before that, we're going to learn that what are the things present in a number. Suppose we take a number like, let us suppose a number 2721. Since we have already talked before that 2721 can be written in the form of, since it is a decimal number, so how do you represent it, how do you differentiate that it is a decimal number or an octal number or a hexadecimal number? You differentiate with a base. So this is the base. This base makes identification that 10 represents decimal, so 2721 is a decimal number system, falls under decimal number system. So 2 into 1 2 3 4. So if you count from the very left to right, so 0 1 2 3, these are the positions and these are the phase values. 2 7 2 1 the phase values. So 2 is the phase value and 3 is the position value. Now if you write in the form of the expanded form, 10 to the power of 3 plus 7 into 10 to the power of 2 plus 2 into 10 to the power of 1 plus 1 into 10 to the power of 0. As we all know, this is the phase value and this is the position value. But the thing is that we need to learn something more. The digit which is present at the very right, this is called the MSB, or it stands for most significant bit, and the number which is at the very left is the very left in terms of going from here to here, from left to right. We can say that in the very left, so this becomes your LSB, or least significant bit. Now moving forward, we need to make interconversion between the different bases. So the first thing we are going to learn that conversion of decimal to binary. Since binary has only 2 digits, that is ones and zeros, so it has a base of 2, and since the decimal has 10 different digits, so it has base of 10. Now we are going to convert. So let us take an example for a value of 16 base 10. So how we are going to convert that into binary? We are going to do LCM with 2. So 16 LCM. So 2 8s are 16. What is the remainder? 0. 2 4s are 8. What is the remainder? 0. 2 2s are 4. What is the remainder? 0. 2 1s are 2. So what is the remainder? 0. So now writing from the very bottom to top, we can say that 1 then 4 zeros represent 16 in binary form. Let us take another example to understand a little bit more. Suppose 277 base 10. So 277 base 10, let us convert it. So 277, now division with 2, so 2 1s are 2 and 38 is 76, so remainder is 1. 2 6 are 12 and base is 19, so remainder is 0. 2 34s are 68, so remainder is 1. 2 17s are 34, remainder is 0. 2 8s are 16, so remainder is 1. 2 4s are 8, so remainder is 0. 2 2s are 4, remainder is 0. 2 1s are 2, remainder is 0. Now starting from the very bottom to top, so what you are seeing, 1, then 3 zeros, then 1, a single 0, then another 1, then a single 0, then another 1. So this is the binary equivalent of 277 base 10 to this one. Now we are going to see that how to convert the decimal number system of the fractional part. Conversion of decimal number system, decimal number with fractional part to binary. So let us see. Let us take an example for 20.25. So we need to convert this number with a fractional part to binary. So we can divide these two parts into two forms, 20 and 0.25. So first of all, we are going to convert this 20 in the normal way I have learned just a few minutes before. 20, 2 10s are 20, remainder is 0. 2 5s are 10, remainder is 0. 2 2s are 4, remainder is 1. 2 1s are 2, remainder is 0. Right from the bottom to the top, so we are getting 1 0 1 0 0. So this is only the 20 part. Now we are going to convert the 0.25. So how do we convert this? 0.25 we need to multiply with 2 for the decimal part. So 0.25 into 2 is 0.50. So what you are going to see here is 0 only, so we are going to write 0. Then again we will take the rest of the part and write here 0.50 into 2, it is 1.00. so we will write here. Now there is nothing present in the decimal, so we are going to leave that aside and write from the top to bottom, so 0.01. So now we are going to add these two things. So what you are getting, 10100.01. so this is the binary equivalent of this fractional value. Let us take another example to explain this. In case, you have to remember that there will be some cases where there will be not a value ending with 5. So in that case, what we are going to do for that, let us see. Let us take an example of 257.343. So we are going to convert this decimal number to binary. So we are going to separate these two parts. 257.343. So 257, let us convert it to 128s are 256. So remainder is 1. 264s are 128, remainder is 0. 232s are 64, remainder is 0. 2 16s are 32, remainder is 0. 2 8s are 16, remainder is 0. 2 4s are 8, remainder is 0. 2 2s are 4, remainder is 0. 2 1s are 2, remainder is 0. From the very bottom to the top, so 1, then how many zeros are there? 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. Let us again count 1 2 3 4 5 6 7. Okay, there are 7 zeros and last one. So this is the first part. Then again 0.343 we have to do that. So 0.343 into 2 is 0.686. so 0 is there, and take out the rest of the part. So 0.686 into 2 is how much? 1.372. so 1 is already present here. So let us write that and take out the rest of the part. 0.372 into 2, so it is again 0.744. take out the 0 part and place it here, and take out the rest of the part. So the rest of the part is 0.744. just only the rest of the part, just the decimal part. Twice it again, then what you are getting? 1.488. place it here and take out the rest of the part. 0.488 into 2 is 0.976. So you are seeing that if you continue to multiply with 2, it will go on and go on and go on. So at some point of time we are going to stop. So just remember that if you have gone for 1 2 3 4 5 times, then stop at that position. You don't need to go so far. You can go up to 10 or 10 times also, but it will consume more time and will be very much more accurate, but we need to do these sums quickly. So let us write from the top to bottom. So 0 1, so what is this? 0 1 0 1 0 1 0 1 and again 0, so with the front point. Then what? We need to add this part, this two part. So what we are getting? 1, then 7 zeros, 2 3 4 5 6 7, 1 point, then 0 1 0 1 and then 0. This is your final answer. Now moving forward, now we are going to do that just reverse thing, conversion of binary to decimal. Okay, so let us take an example. Suppose 1 1 0 1 1 0. So these are example of a binary. So you can see here that 0 1 1 0 1 1 are the phase values. So what are the positions? So starting from the very end, we can see that the positions we can write here like this: 0 1 2 3 4 and 5. Okay, now we're going to write in the form of like this: 1 into 2 to the power of 5, since we are multiplying with 2y because it is a base of 2. So 1 into 2 to the power of 5 plus 1 into 2 to the power of 4 plus 0 into 2 to the power of 3 plus 1 into 2 to the power of 2 plus 1 into 2 to the power of 1 plus 0 into 2 to the power of 0. So 1 into 2 to the power of 5 is 32. 2 into 2 to the power of 2 to the power of 4 is 16. 16 times 1 is 16. Anything multiplied by 0 is 0. 2 to the power of 4 is 4. 4 times 1 is 4. 2 to the power of 1 is 2. So 2 times 1 is 2. And anything multiplied by 0 is 0. So ultimately, if you add up all this, what you are getting? 32 16 plus 4 is 20. 20 plus 2 is 22. 22 plus 32 is 54. Base 10. Okay. Let us take another example. 1 0 0 0 1 0 1 base 2. So again, let us write the positions from the very end. 0 1 2 3 4 5 and 6. So let us write 1 2 to the power of 6 plus 0 into 2 to the power of 5 plus 0 into 4 to the power of 2 to the power of 4 plus 0 into 2 to the power of 3 plus 1 into 2 to the power of 2 plus 0 into 2 to the power of 1 and 1 into 2 to the power of 0. So 2 to the power of 6 is 64. 64 times 1 is 64. So these are all zeros. So anything multiplied by 0 is 0. So 0 plus 0 0 plus 0 plus 0. Okay. Then 2 to the power of 2 is 4. 4 times 1 is 4. 0 into 0 is 0. And anything to the power of 0 is 1. So 2 to the power of 0 is 1. 1 into 1 is 1. So we can say that 64 plus 4 is 68 plus 1 is 69 base 10. So this is how we convert a non-fractional binary number to a decimal number. Then moving forward, conversion of fractional binary number system to decimal number system. Now let us take example. Suppose 1110.1101. Now how do you write this? So look here, the positions are from, just take it from here. The positions are what? 0 1 2 3 and 4. From the point side we can say that it is 1 into this, the position is -1 -2 -3 and -4. Now we're gonna write like this: equals 2 into phase value is 1, so 2 into 4 plus 1 into 2 to the power of 3 plus 1 into 2 to the power of 2 plus 1 into 2 to the power of 1 plus 0 into 2 to the power of 0. Then carry forward 1 into 2 to the power of minus 1 plus 1 into 2 to the power of minus 2 plus 1 into 2 to the power of here is only 1, here only 0 because this point minus 3 plus 1 into 2 to the power of minus 4. So it becomes 2 to the power of 4 is 16, so 16 times 1 is 16. 2 to the power of 3 is 8, so 1 times 8 is 8. 2 to the power of 4 is 4, 1 times 4 is 4. 2 to the power of 1 is 2, 2 times 1 is 2. And 0 is anything multiplied by 0 is 0. Then we can write like this, since we have already studied in your class 9 that the chapter exponents, so from that experience you should be knowing that what will be this. So 1 by 2 to the power of 1 plus 1 by 2 to the power of 2 plus, so anything multiplied by 0 is 0, plus 1 by 2 to the power of 4. Now if you add up, 16 plus 8 is 24, 16 plus 8 is 24, 24 plus 4 is 28, 28 plus 2 is 30, 30 plus 0 is 30 also. So 1 divided by 2 is 0.5. So then 1 divided by 2 to the power 4 is 0.25. It is already 0. And then 1 divided by 2 to the power of 4 is what? 2 to the power of 4 is stands for 0.0625. Now if you add up all, what becomes? It becomes approximately 30.5. 30.5. So 30 plus 0.5 plus 0.25 plus 0 plus 0.625. So basically the answer will be your 30.8125 base 10. So basically you are converting a fractional binary number system to a decimal number system. Now let's take another example. Suppose 110.111. So what are the positions? Let us zoom in. So from the here it is 0, 1, 2, 3, and from the after the point value it is 1, minus 1, minus 2, and minus 3. So we write like this, equals 1 into 2 to the power of 3 plus 1 into 2 to the power of 2 plus 0 into 2 to the power of 1 plus 1 into 2 to the power of 0 plus 1 into 2 to the power of minus 1 plus 1 into 2 to the power of minus 2 plus 1 into 2 to the power of minus 3. So it becomes 2 to the power of 3 is 8, so 8 times 1 is 8. 2 to the power of 2 is 4, so 4 times 1 is 4, plus it is 0. 1 into 2 to the power of 0 is 1, plus 1 by 2 plus 1 by 2 to the power of 2 plus 1 by 2 to the power of 3. So let us sum up this. It becomes here 13, and this half becomes 0.5. this becomes 0.125, 0.25, and 1 by 2 to the power 3 is 0.125. Sum it up all, so it is 0.5 plus your 0.25 is 0.75. So 0.75 plus 1.25 is 13.875 base 10. So this is the interconversion of fractional binary number system to your decimal number system. Moving forward, then we are going to see that conversion of decimal to octal, number system. So let us take an example. Suppose 317 base 10. So similar to the decimal to binary number system. So in binary number system, we did LCM with just 2. Here we are going to do LCM with 8. So 317 divided by 8. So what is the closest number you can get? So the 317 is 830 is 240. Then 833 is. So if you continue to do that, we will be getting a number close to 839. So 839 is 18 to 39 is 312. So remainder is 5, because 8 times 39 is 312. So 370 minus 312 is 5. So then 8 times 39. So 8 times 39 is 39. So the closest number you can get is 4. And then again, if you multiply with 5, it becomes 40. So 8 times 39. So 8 times 4. So remainder is 7. So since the number is less than 8, and we cannot do that again, so from the very bottom to top we're going to write, so 457 is the octal equivalent of the decimal. So we write with base 8. Let us take another example. Suppose 217, a big number. So let's do this. So 2417 divided by 8 is 300. So no, then you will not be able to do that. So 300 suppose. So 300, so we can put it like this, 302. So base is, so remainder is 1. Then again 8, so 840, 839, 838 is 304. So 838 is 304. Then again 837 is 296. So again base 6. Let's again do this. 824, 832 is 256. Let's go closer. 280 and 7 is 296. So 37 is 296. So remainder is 0. Then again continuing with the division part. 8 4 is 32. so remainder is 5. So the number is less than 8, so we cannot do that again. So from the very bottom to top we are getting 25061 base 8 is the octal equivalent of this number. Now fractional decimal number to octal equivalent. So let us see. Let's take an example. 324.68 base 10. So let us see that equals, we are going to, like the binary number system, where we are going to split this to the two parts, 324 and 0.68. So 324 divided by 8 is what? 40. So 40, remainder is 4. So 8 5s are, remainder is 0. From the bottom to top, since the number is less than 8, so 504 is the first part, and then the remaining part shall be multiplied by 8. So 0.68 into 8 equals to 5.44. Take out this part and place it here. So the rest of the part, 0.44 into 8. So 0.44 into 8 is 3.52. Take out this part and place it here. 0.52 into 8 is 4.16. So this is 4. 0.16 into 8 is 1.28. So it is 1. So as we have already told in the previous video that somehow if you're not getting the end point, so you need to stop at certain level. So let us do again. 0.28 into 8 equals to 2.24. Take this part, place it here. So ultimately on the very first top we are getting 0.53412 base 8. So add these two parts. So ultimately you are getting 504.53412 is 8. So fractional decimal number to octal equivalent. Now let's take another example. Another example, a small example to understand that a better part. So suppose 30.125. So let us do this. Split it up into two portions, 30 and 0.125. So let us do the first part, 30. So 8 4s are 8, 3s are 24. So base is 6. So 36 base 8, the first part, and the remaining part 0.125 times 8 is equals to 1.00. So take it out and place it here. So since there are no number present here in the point, so place, so it becomes 0.1 base 8. So again add it up, we are getting 36.1 base 8 of octal equivalent. Now we are going to see that conversion of decimal to hexadecimal. Let's take an example. Suppose 256 base 10. So since hexadecimal has a base of 16, so we are going to do the LCM with 16. 256 divided by 16 is 16 6 256. Again, so remainder is 0. Again 16 1 is 16, remainder is 0. So from the bottom to top it is 100 base 16. Okay, let us take another example. Suppose 1 2 3 4 base 10 to hexadecimal equivalent. So 1 2 3 divided by 16. So 16, so let us do this. 16 into 70 is your 1120. So let's push forward. 16 to 80 is 1280, so it is quite more. So 16 into 79 is 1264, is still more. 16 into 78, so it is, so 16 into 78, 75, 78 is 11248, still not there. So 16 times 77 is your 1232, so base 2, so remainder is 2. Again do this. 16 4s are 64, 16 5s are 80, so 16 4s are 64, so 77. So 77 minus 64 is 13. Now what we have learned before, that we can't represent 13 like that, so we need to represent in the form of your digits. So what we have learned in the previous that a equals to 10, b equals to 11, c equals to 12, and d equals to 13, e equals to 14, and f equals to 15. So 13 can be written in the form of d, so we are going to write d. So on the very bottom to top, so 4d2 base 16. Let us take another example to be clear a little bit. So 1228. Let's take another example. So 1228. 1228. So let us write 16 1228. So let us do counting a little bit. So 16 times 76 is your 1216. So 1228 minus 1216 is your 12. So 12 is what? 12 is C. So we will write C. Then 16 4s are 64, 16 5s are 80. So 16 4s are 64. So again 76 minus 64 is your 12. So it is again C. So from the very bottom to top, it is 4cc base 16. Alright. So decimal to hexadecimal, normal way. and then fractional decimal to hexadecimal. So let us take an example. Suppose a decimal number with some decimal fractional part. Suppose 272.16. So we need to convert this to hexadecimal equivalent. So what we need to do is to split it up, 272 and 0.16. Now 272 as usual division with 16, so we can say that 16, so 16 tens are, no, it won't happen. So 16 into 17 is 272. So 16 to 17 is 272. So remainder is 0, and 16 ones are 16. So remainder is 1. So we getting a value of 110 base 16, which is this part. Now we need to think about this part. How do we deal with this? We need to multiply this 0.16 into 16. So 0.16 into 16 is approximately 2.56. So we need to take this part apart and place it here. Then with the rest of the part, 0.56 into 16 equals what? 0.56 into 16 is 8.96. So take this apart and place it here. So 8. Then rest of the part, 0.96 into 16 equals 0.96 into 16, because equals 15.36. So 15 is what? 15 is in hexadecimal is FF. So if we move forward with another part, so since it is a non-5 ending part, so we cannot stop at certain point, because it will go on and go on and go on. So we need to stop at certain point, which we have learned that at least 5 decimal points we have to show up. So 0.36 times 16 is 5.76. So 5 and 0.76 times 16 equals to 12.16, which is, so we will take the 12th part, and 12 is what? 12 is C. A is 10, B is 11, C and 12 is C. So the values, so the value standing is from the top to bottom order is 28FC. 28FC. So ultimately our value is standing at is 110.28 FC base 16. Let us take another example. 100.50 base 10. Let us convert, split up into two parts, 100 and 0.50. So 100, 16 6 ja 96, and remainder is 4. So from top bottom to top is 64, and the 0.5 part multiplied by 16 is 8. So 8 So there are no remainder part remaining, so we will do this. So this will become 0.8 since it is a point part only. So let us add it up. So it will become what? 64.8 base 16. Okay, now we will do conversion of hexadecimal to decimal. Let us take an example. Suppose FE. Now F is what? F is, so let us first of all let us write the positions. E is 0 and here is 1. Now we already know that E is 14 and F is 15. So we need to do this, that F is the face value times 16. Since it is hexadecimal, we are converting back to decimal, so we need to multiply with 16. So 16 to the power of 1, this is the position. This position we have kept it here, plus E multiplied by 16 to the power of 0. So ultimately F is 15 into 16, E is 15 and 16 to the power of 0 is 1. So 240 plus 15, so answer is 255 base 10. Alright, let us see another example. (3DF). So base 16. So this position is 0, this position is 1, this position is 2. So 3 into 16 to the power of 2 plus D into 16 to the power of 1 plus F into 16 to the power of 0. Alright, now D is what? D stands for A is 10, B is 11, C is 12 and D is 13 and F is 15. So 3 into 16 square is 256 plus 13 into 16 plus 15. 16 to the power of 0 is 1. So 3 times 256 is 768. 13 times 16 is 208 and 15 times 1 is 15. So let us sum it up. So it will ultimately 768 plus 208 becomes 976 plus 15 is 991 base 10. Okay, let us move forward. Fractional hexadecimal to decimal. Let us take an example. Suppose FF dot 1A. Now F is what? 15. A is what? 10. There is 16. So let us convert. Same process as before. We need to split it up into two parts, FF and 0.1A. So F first we need to do the part which is before the decimal. So FF. So now F is at what position? F is at 0 position. This is at 1 position. This is at 1 minus 1 position. This is at 2 position, minus 2 position. So F into 16 to the power of 1 plus f into 16 to the power of 0 plus 1 into 16 to the power of minus 1 plus a is 10, so a into 16 to the power of minus 2. So 15 is 15 into 16 plus 15 into 16 to the power of 0 is 1 by 16 plus 10 into 1 by 16 to the power of 2. So 15 into 16 is 240 plus 15 plus 1 by 16 is 0.0625 plus now 1 by 16 is 10 divided by 256 is 0.0390625. So let us sum it up. So it is ultimately becoming 240 plus this 255.0.0625 plus 0.0390625. So it is 1015625 base 10.